Hello everyone, welcome to our lecture on NumPy Arrays. In this one, we're going to have a look at the various different ways of creating arrays inside of NumPy, as well as learning about some of the associated array methods and attributes available for us to use. Let's move over into our Jupyter Notebook and get started. Before we start, all of the notebooks for this lecture can be found within the Section 11 NumPy folder. And then within here, there is a notebook for each lecture. I've put them into separate notebooks so that they're easier to access the code for each lecture. And we'll start with our first one here on NumPy Arrays. Like last time, I'll start from a new notebook and then work through the code inside of the course notebooks, explaining the code as I go along. Before we're able to use any of the NumPy library, we'll first need to import it. This is something that we looked at towards the end of the last section, so hopefully you can remember how we did it. We'll start by saying import and then our library name, which is NumPy, and then you can just say as np, which is the typical alias that you'll see used for NumPy. When it comes to NumPy arrays, there are two main types to be aware of, and these are either the one-dimensional array, which are called vectors, or the two-dimensional array, which are called matrices. But both of these fall under the category of n-dimensional or NumPy arrays. Let's start by looking at how to create a NumPy array from a regular Python list. We'll start by creating a regular list with a few numbers in it. And then if we check the type of this with the type function, we can see that it's just a regular list. We can then use the NumPy array function to cast this into a NumPy array. So we'll call np.array and then pass in the name of our list. And if we run this, we'll get our list but returned as a NumPy array. And then we can assign the result of this to a variable and then call our array from this variable. If we check the type of our variable here, we'll see that it actually returns the numpy.ndarray data type as opposed to a list. So this confirms that this is now a NumPy array. Instead of passing in an existing Python list, we could also just pass in our numbers directly into this function, and that'll work fine too. Okay, let's now introduce a couple of different attributes that we can use to view information about our NumPy arrays. Something special about NumPy arrays is that they have something called a dtype, which is just short for data type. We can view the data type of our array with the .dtype attribute. And by the way, the reason that this is an attribute and not a method is because it doesn't actually modify our array in any way. It just returns some information about it. And we can see here that our dtype or data type for this array is int32. And what this means is that the array is basically casting and forcing every value or object that's put inside of this array to be of this data type. So in this case, it's int32. We know that int is short for integer, but this extra 32 denotes how many bits this number is assigned. So typically, we'll either see int32 or int64. If we create another NumPy array, which I'll just call floating point array, but this time put some decimal numbers inside of it, we'll check the dtype of this array. We'll see that the dtype or data type of this array is a float, as this is a floating point number. We also have an attribute called ndim, which will return the number of dimensions that our array has. Throughout this section and the rest of the course, we'll be working primarily with one-dimensional arrays, which are called vectors, and two-dimensional arrays, which are called matrices. And this array here has one dimension, so we can say that this is a one-dimensional array, or vector. Another very helpful and important attribute is shape, and this just returns the shape of our array. The output of this attribute is just a tuple, which shows the size of each dimension for the array. Our array has 5 elements, so it will return a 5 here. And as this is only a one-dimensional array, it'll just return one number. But we'll see what a 2D array looks like shortly. And then we also just have size, which returns the overall number of elements inside of our array, which in this case is simply 5. And this slide here will give us a helpful overview and summary of what we've just learned. To create a NumPy array, we first need to use the np.array function. And then inside of the parentheses, we can pass in our argument, so what number we want to cast to be an array. In this example here, we create an array containing 4 numbers, so 1, 2, 3, and 4. And then we can confirm that this is an array with the type function. Below this, we have the 4 attributes that we covered, which were dtype, ndim, shape, and size. Of these, dtype and shape will be the most helpful and most commonly used. So dtype checks and returns the data type of the values inside the array, and then shape just returns the size of each dimension in our array. This is now a good time to take a look at a big advantage of NumPy arrays as opposed to regular Python lists. In the last lecture, which was our introduction to NumPy, I mentioned something called element-wise operations. Inside of NumPy, element-wise operations refer to operations that are applied individually to each element inside of an array. To demonstrate this, let's swiftly create 2 regular Python lists with numbers going from 1 to 10 with 5 numbers in each list. And let's say that we wanted to add these 2 lists together. So 1 plus 6, 2 plus 7, 3 plus 8, and so on. We might try just saying list 1 plus list 2. But if we run this, our result is actually just a concatenation of our 2 lists. So not the actual numbers or values added together. With a regular Python list, adding these 2 lists together would require the use of a loop, which is not only quite slow computationally, but is also quite time consuming to make. With NumPy, all we have to do is simply add the 2 lists together. So we have our 2 NumPy arrays here, array 1 and a floating point array. And if we just say array 1 plus a floating point array, and I've clearly made a mistake here somewhere along the way. So what I've done here is when I created my floating point array, I've accidentally only made it with 4 elements as opposed to 5, which is what I should have done. We can see down here that in our error message, it tells us that the operands could not be broadcast together with shapes of 5 and 4. I'll just go ahead and add another element to our second array. Then if we rerun our array cell to update the arrays, we can go back to our addition and then that'll work fine. So now that we've fixed this small bug in our code, it'll then add each element or the value at each index together. And we could also multiply, subtract, divide, or use any other operation that we wanted to here. Let's now move on to looking at 2-dimensional arrays, so the matrix array type. To create one of these, we need to pass in multiple lists to our np.array function. Let's create a variable called matrix, which will be equal to np.array, but then inside of our parentheses, we'll pass in 2 lists. So our first list will be 1, 2, 3, and then our second list will be 4, 5, and 6. And note here that as we've passed in multiple lists, we also have to wrap our lists inside of square brackets too. If we take a look at this variable, we'll see that we now have a 2D array, and this is shown in 2 main ways. Most obviously is the fact that we now also have another row inside of our array, but a more reliable indicator, as we'll see later on, is the fact that we now have 2 sets of square brackets shown on the opening and closing ends of our array. With a 1-dimensional array, as we can see up here, we get 1 set of square brackets, and then if we had a 3-dimensional array, we'd have 3 sets of opening and closing square brackets. Let's now have a look at the shape and size attributes for our matrix. Starting with shape, we'll see that we have a shape of 2 and 3. The first number in our tuple represents the number of rows, and the second number is the number of columns. And make sure to remember this, as it's a very helpful thing to know just off the top of your head. If we check the size of this array, we'll get a value of 6 because there are 6 elements inside of this list. And let's just quickly go over and recap what we've learned here. To create a matrix, we can use the same np.array function, but instead of passing in a single list, we can actually pass in a list of lists. We can see that for this matrix here, it's got a shape of 2 and 4. And that's because it has 2 rows and 4 columns, as we can see at the top here from the output of our variable. Unlike last time, where we just had 1 dimension, this time our endim attribute returns 2, as we have 2 dimensions in this array, because there's both rows and columns. And then finally, size will again return the number of elements inside of the array. Okay, so we now know how to create our own arrays manually. Usually though, you'll use one of NumPy's built-in functions to do this automatically for us. And we'll have a look at a few of these functions now. The first and most common way of creating NumPy arrays is by using the numpy.arrange function. And this returns a range of evenly spaced numbers within a given interval, much like Python's built-in range function. We can go ahead and say np.arrange, and then in here we can pass in our start value and our stop value. So we'll start at 0 and then stop at 20. So this will then go all the way from 0 and then up to, but not including 20. So actually 19. We could also pass in an optional third argument for the step, and this is just what we want the number to go up in. So if I added in 2 here, our numbers would now go up in steps of 2. And this function works in pretty much the exact same way as Python's built-in range function. So if we wanted our final value to be 20, we could just set our stop value to be 21. And arrange is probably one of the most useful functions for quickly and easily creating arrays in NumPy. Next, we have the zeros and ones functions, and these just create either arrays of all zeros or all ones. For example, we could go ahead and say np.zeros, and then for our parameters, we can pass in either a single digit, which will return a vector, so a one-dimensional array, or we could pass in a tuple, which will return a 2D matrix, like we can see here. So again, our row dimension comes first, and then next we have our number of columns. On the flip side of this, we also have np.ones, which works in the exact same way, but will instead create an array of all ones. Another very helpful function that we have available for creating lists is linspace. This returns evenly spaced numbers, but over a given interval. So this sounds quite similar to arrange that we looked at before, but these functions do 2 very different things. We'll go ahead and say np.linspace, and then we'll pass in a start and a stop value. So I'll go for a start of 0.1 and then a stop value of 1. And then let's say that we want 10 evenly spaced numbers between these 2 points. We could just put a 10 in here for our third argument, and then if we run this, it'll return a 1D vector containing 10 evenly spaced numbers from 0.1 to 10. If, for instance, we wanted 20 numbers, we could just change our 10 to 20. And something to note here is that even though this looks like it could be a 2D array, as it's on multiple different lines, we only have one set of square brackets, so it's actually a one-dimensional vector, which is why it's better to go by these square brackets or one of the attributes we looked at, as opposed to purely how many lines it covers. Next, we'll move on to looking at how to create random numbers inside of NumPy. There's a couple of different ways to do this, but we'll look at the 3 main and most common functions, which are rand, randn, and randint. Starting with rand, this function creates an array of a given shape and then populates it with random numbers from 0 to 1 that have a uniform distribution. What we'll do is we'll call np and then random, and this will then let us access all of the random functions available inside of NumPy. If we press tab, it will bring up a list of all the different options we have for our random functions. And as you can see, there's quite a lot here. We'll go for rand, and then the only parameter that we need to provide is the amount of random numbers that we want. So I'll just put 4 in here, and then if we run it, it will return a one-dimensional array of 4 random numbers between 0 and 1. And these numbers here have a uniform distribution. And a uniform distribution is just a type of probability distribution in which all outcomes are equally likely. If we wanted to return a matrix or 2D array, we actually don't need to pass in a tuple. We can just pass in 2 numbers separated by a comma. Next, we have rand n, and this returns a sample or samples of a standard normal distribution, as opposed to rand, which returned a uniform distribution. A normal distribution, sometimes known as a Gaussian distribution, is a probability distribution that is symmetric near the mean, showing that the data near the mean is more common in occurrence than any outliers. It's got the same syntax and arguments as rand, so we'll go ahead and say np.random.randn, and then for our arguments, we'll pass in how many numbers we want. So I'll go for a 2D matrix with 4 rows and 4 columns. And these numbers here are normally distributed, which we can have a look at when we come to visualize our data later on. We'll finish off our random functions by looking at randint, which will return random integers in a given range. We can go ahead and say np.random.randint, and then if we have a look at our Shift tab documentation, it'll ask us for a low value, a high value, and then the size, which is just how many numbers we want to return. So I'll provide a start of 1, and then a high of 100. If we run this, it'll return a single number, but if we wanted more, we could add it in our third argument. So I'll just put 5 in here, and then this will now create an array of 5 random numbers between 1 and 99. So just to clarify this, the start or low value of 1 is inclusive, so this number could be included, but our high value, in this case of 100, is not. The maximum value we could get here would be 99. Okay, now that we've looked at how to create arrays, let's have a look at some of the methods that we have available on them. Just like with strings, lists, and dictionaries that we looked at in the last section, NumPy arrays also have methods too. To demonstrate our array methods, we'll first use one of the functions that we've just learned about to create a new array. So I'll use the arrange function to create an array of 40 different numbers, starting at 0 and finishing at 39. With our array made, the first method we'll look at is reshape. And this just allows us to modify an existing array and reshape it. So if we look at the array that we just made, we'll see that it's currently a one-dimensional vector, as illustrated by the single brackets. And we can also confirm this with either the shape or endim attribute. I'll just use shape. Let's now call the reshape method on our array, and then we'll pass in our arguments, which will be the new dimensions. So for instance, if we want this array, which contains 40 values, to have 4 rows and 10 columns, we could pass in 4 and 10. And then if we call shape on this, we'll now see that rather than having 40, we now have 4, 10. So 4 rows and 10 columns. As an alternative to reshape, we also have flatten. And this will return a 2D array, but collapsed into one dimension. So basically turns a matrix into a vector. Let's go ahead and create another matrix here, which I'll do with the np.random.randN function. I'll create a variable called npMatrix, and then this will just be equal to np.random.randN, and then just with 2 rows and 4 columns. And then if we have a look at the shape of our matrix, we can confirm that it's got 2 rows and 4 columns. Let's create a new variable, and then we'll say that it's equal to our npMatrix, but with the flattened method called. And if we now print the contents of our actual variable, we only have one set of square brackets, which tells us that this is now a one-dimensional array. And we can confirm this by checking its shape, and yep, we can see here that we now just have one dimension containing 8 values. Finally, we'll look at max, min, argmax, and argmin, which can be used to return the maximum and minimum, as well as the index position of the largest and smallest numbers in an array, respectively. Let's use randint to create an array containing 10 random variables between 1 and 100. And then, if we have a look at the contents of our NumPy random array, we've got 10 random numbers. And if we call max on this, it'll return the largest number inside of our array, as we can see here. Of course, we also have min, which returns the smallest number inside of the array. Argmax and argmin will return the index position of these numbers as opposed to the actual numbers themselves. So you can see that our largest number here is at index position 2, and if we call argmax on our array, it'll also return index position 2, which is where our largest number is located. And then argmin will do the same, but for our smallest value. Okay, and that there wraps up our lecture on NumPy arrays. In the next one, we're going to have a look at indexing and slicing our NumPy arrays, as well as something called broadcasting. Thanks everyone, and I'll see you all in the next lecture.